two turtles mounted on a boat-like surface, completely symmetric one way or the other. And you can position the turtles in any way you like. They can be facing each other. They are in love. That's very beautiful. And you can spin them one way or the other way. Or they might have had a tiff, fighting, don't want to talk to each other anymore, but still you can spin them positively or negatively. Or maybe one of them is in love with the other, but alas, affection is not reciprocated. You can still spin them clockwise or counterclockwise. So far, no surprise. However, if you position the turtles like so, thereby changing the symmetry pattern, you see, you no longer have this Z2 cross Z2 symmetry. Sorry, I mean America, Z2 cross Z2 symmetry. But there is a point symmetry so that the center of gravity is smack in the middle still. That hasn't changed. Then, you know that turtles like to walk forward. You have never seen a turtle, I dare say, walking backwards. So if you ask them politely and gently, of course, because these are sensitive animals, to please go forward, they are willing to oblige us by spinning smoothly forward. But if you try to force them to go backwards, they say, no, 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 we don't want to go backwards, and spontaneously reverse the spin. No, 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 we don't want to go backwards and it is not the question of left or right, because now if you position them in the Z shape, yeah, what used to be the reluctant direction, now going forward, they are willing to oblige us. But what used to be the favored direction, they are going backwards, so they say, really, we don't want to do this. You are all wondering what happens if I position the turtles like this. Then let's spin them clockwise as seen from above. This turtle would be going forward, this one would be going backward, this one would be happy, this one unhappy. Happiness and unhappiness cancel each other, so one vote each, very democratic turtles. And if you try to spin them the other way, happiness and unhappiness reverse, and they also can spin. Wonderful creatures, those turtles. Well, you know, this phenomenon was recorded in literature more than 100 years ago, and towards the end of the 19th century. And since then, lots and lots of papers have appeared. Most of them, however, were based on this kind of object. This is widely available, a rattleback it's called, and we shall come back to the name later on. And this one, I think I bought from the Boston Museum of Science more than 20 years ago. And it does have this chiral preference, chiral as in handedness. You want to spin one way, but try it to spin the other way, it stops and reverses. Clearly, the turtles are better because, first of all, they're turtles, but also it's an infinite, parametric family of those toys. But one of the things that misled people is that, you see, this toy has a strange surface of contact. If you look close, there is a kind of mountain ridge that runs in an S shape, which makes the surface of contact asymmetric. And many people were led to believe that this asymmetry of the surface, strange skewness of the surface, had something to do with the behavior. Whereas it has nothing to do with the skewness of the surface. It can be completely symmetric. What matters is where the heads are. In other words, how the mass is skewed distributed. Okay. In order to make that point, here is a prototype. Can you zoom in a little more? Yeah, thank you very much. Here is a prototype that was made in Paris. It's completely symmetric as far as the shape is concerned. Not only that, it's symmetric front and back. However, it does have a preferred direction of spin. It wants to spin clockwise, as seen from above, and anti-clockwise, counterclockwise, it stops and reverses. That's very strange. What's happening? But when I rub it against my shirt, you remember which way it was spinning? It was spinning clockwise, but now you want to spin counterclockwise, and clockwise, it refuses to spin. I can rub it against my hair, and that also reverses the chirality. It's now spinning clockwise like before, but if I rub it against my jeans, nothing happens. It's still spinning around. And Elwyn, sitting in front, has carefully noted that when I take this up and then rub it against my shirt, when I put it down, I do this. What's hidden inside is a lead bar, which has been skewed a little like that with respect to the geometrical axis. So that in this position, it wants to spin one way because the turtles effectively are sticking their heads out like this. But when I flip over, having, of course, rubbed it against my shirt, the turtles are sticking there. So you see the mass distribution, skewness, that has everything to do with the thing. In more technical terms, it's the ellipsoid of inertia, which should be misaligned with the geometrical axis. Now, I'd like to show you one observation which has eluded lots of people, and in fact, which turns out to be the key to cracking this motion. I'm not going to do the mathematical analysis today, but this is the key observation. If you think of this boat, well, there are many different ways in which a boat can rock. It can go back and forth, or sideways. The forth and back, that kind of rocking is called pitching in nautical terminology, to pitch. And sideways is called rolling. That's the rocking that makes most people seasick, rolling. And of course, it can spin one way or the other. And we note that if you excite pitching, that is by tapping here, the turtles spontaneously start moving forward. If I position the turtles like this, they start spontaneously moving forward in this direction. By the way, you can make this kind of thing at home. If you happen to have kept an old-fashioned telephone handset, you know, not the modern one with a flat bottom, but the strictly convex-shaped telephone handset, disconnected from the cord and attached hefty masses with scotch tape, like batteries, and then if you put it on the table and tap, it will spontaneously start spinning one way rather than the other way. Now, it's amazing to me that many people have studied this, but very few have tried rolling instead of pitching. What happens if we roll the turtles? Well, again, a little bit of revision. Pitching makes them go forward, and if you try to force them to go backwards, pitching gets excited, followed by the reversal of the angular momentum. All right. We shall now excite rolling for the first time at MSRI. When I excite rolling, turtles start going backwards. They are behaving like reverse turtles. So I was cheating all of you a moment ago. You see, I said that if you spin the turtles forward, they are stable, but that's not true. Turtles start rocking their heads, that's rolling, so as a result, even from the forward motion, they can reverse. In many places in literature, it is claimed that the forward motion of this toy is stable, backward unstable, but that's false. In fact, both motions, both directions are unstable. It turns out the exponents of instability are different, forward, backward, different, but it's always unstable, so that if the friction does not kill the motion prematurely, you can have multiple reversals, back and forth, back and forth. One of the world records, in fact, I think it's been broken by now, was held by those turtles, which was achieved on a marble top table in a cafe next to the British Museum in London. And they reversed, I think, 5 times. And I wanted to buy that marble top table with a research grant, but somehow the research council didn't say yes. So those are the great turtles. Chiral behavior. Another chiral toy. That's a little beach ball, and the seal comes to play. I went to admire the sea lions in San Francisco. And when it comes to play, I'm not doing this or doing this. I'm not inputting any rotational pattern. Nonetheless, when the seal comes directly towards the ball, mysteriously the ball starts spinning. And remarkably, from whichever direction it comes in, isotropically the ball spins. Mind you, the ball can spin very, very fast. You see, I'm barely pushing the seal, but look how crazy the ball goes. Now, thank you very much. You have all noticed that it has to do with the magnet. But then the question is, magnet, so what? How do you position the magnets inside? After all, if you have 2 magnets like this, then they'll just pull each other, and then there will be no rotation. And if you have parallel magnets, they'll repel, there will be no rotation. How do you arrange the magnets so that from whatever direction you always get the same spin, seen from the top, always clockwise? An interesting inverse problem. Here is a stone that I had. Again, it has a chiral preference. If I tap, it starts spinning one way. The other direction is very weak, so you can barely feel it, but that's how it is. Okay, now, all that is wonderful, and I shall now, this seems to have died, so how do I wake this up? Here it is, to the laptop. Please, booth laptop, thank you very much. Is it working? Okay. Now, a little exegesis on the linguistics that I would like to comment. What happened to, excuse me, I'm going to start going in this direction because I don't have a clock and I would like to keep track of the time, and I don't have a watch either. Okay. Yeah, I would like to have, here is my watch, sorry. Okay. These toys have been variously called rattleback, wobblestone, and sometimes celt. Now, if you look in dictionaries, the story that's told is that celt comes about because many archaeologists have found strange stones that had this chiral dynamical behavior in Celtic villages of 2,000 years ago. Maybe they were used as talismans, maybe they were used to pass judgment, and so on. This story turns out, it's very widespread, but it turns out to be false. The real story is even more remarkable. it goes back to the Vulgata Bible, the first Latin translation of the Bible by St. Jerome, as you know. And in there, the book of Job, chapter 19, section 24, verse 24 says, in Latin translation, Stilo ferreo et plumbi lamina, vel celte sculpantur in silice. As usual, Job is complaining about various things, and he's saying, oh, I wish that my words were engraven in stone. A bit more precise translation is that my words were by an iron pen and lead, or by something that looks like by a celt graven in stone. Celte, it looks like the ablative of the Latin word celtus. Now, there is no Latin word celtus. Never has been. So, on the authority of the Vulgata Bible, people thought, well, that must be some implement that existed in antiquity, which was used to chisel stone. However, if you look in the Hebrew original, it says, Bet barzel veofaret la'ad, that's the critical word, which translates celte, batsur yachatzvun. Now, this la'ad in Hebrew turns out to mean for certain, or in Latin, certe, with an R rather than L. So this word celt has come into existence because of a misspelling in the Vulgata Bible, and then the Celtic connection was invented entirely by 18th century antiquarians. So that's the story of the celt. Amazing thing. Okay, so that this class of toys, they have all violated the conservation of angular momentum. So now I'm going to start violating other great laws of physics. Here is an egg. It even says, I don't think the focus is good enough, but it even says EG on the surface in case you had any doubt. Do you know how to distinguish a raw egg from a boiled egg? If you tried to spin it, boiled egg, being a solid body, spins normally, but a raw egg has this liquid stuff sloshing about inside. So it doesn't want to spin very, very much. So you can tell them apart like that. By the way, if you have a raw egg and keep insisting on spinning it, eventually it will yield and start spinning. But then once it spins, try to catch it and release it a fraction of a second later. And you'll see mysteriously that, of course, a solid egg will stay put, as it has now done. But the liquid egg, the raw egg will resume spinning because the angular momentum is carried by the liquid stuff inside, which is quite, but that's not what I wanted to tell you about. What I wanted to tell you about is, have you spun an egg? The experiment that I'm about to show you can work with any boiled eggs on a kitchen table. When you spin an egg, what happens is this. It stands up. Most people have a hard time getting enough energy going with one hand. So I suggest when you do it at home that first you boil the egg, and second, that you hold it with two fingers, one finger and one thumb, and pull in opposite directions, and that gives you enough energy to make it stand up. Remarkable thing. You see, why do we find it remarkable? Because we learn in university in England and in primary school in California that nature wants to lower its center of gravity as much as possible. Nature is lazy, and of course, when you leave it in static state, that's how the egg wants to be. It's lowered its center of gravity. But when it's spinning, there is a general phenomenon that the spinning object in frictional contact with the floor has a tendency to raise its center of gravity. Not often noticed, but generally true. A toy that takes advantage of this phenomenon is this one. You might have seen it, many of you might have. It's hollow inside so that it's weighted effectively at the bottom. So the top wants to look like an apple. If you try to make it look like a mushroom by making it stand upside down, it's unhappy because that's an unstable position, and upside up it is stable. But can we make it stand upside down? Well, you remember that on a frictional floor, something spinning has a tendency to raise its center of gravity. So I'm going to spin it, and it goes pop, upside down. I can do the same thing with my left hand, I can spin it, and then pop. And you're all wondering what happens if I spin it upside up to begin with. Then then it's very stable. And then I can turn it over. It's still very stable. But this stability is only while it's spinning strongly enough. Okay, it's come off the mirror. But when it starts losing the spin, it thinks, so as I'm no longer spinning, I should stop looking weird. and stop looking like a mushroom and go back to being normal, that is looking like an apple with a low center of gravity. Okay, yet another application. If you want to win at golf, I actually have never played golf, but I have published a paper on golf. So you see, I'm a theoretical golfer. And if you're about to putt on the green, and if you really want to win, and if you don't mind losing a friend, then you should replace your friend's golf ball with this one. Because if you try to hit this, it goes like that all over the place. It's a weighted ball, weight at the bottom. So this is stable, upside down it's unstable. Let's grab it and spin it. Then it goes crazy all over the place, but then settles into this steady motion. While it's spinning quietly, where is the center of gravity? Let's grab it. I claim that it's at the top. Indeed, when I release it, it flips over. So tendency to go up, raise the center of gravity when you have frictional contact. I'd like to show you a toy that synthesizes the previous two classes, and this is really something quite shocking to people who work in applied mathematics and physics. This transparent top was made originally by David Acheson at Oxford University by accident, and it's made of some sort of plastic, and it is a tippy top. When I spin, it flips upside down. So it is a fairly efficient tippy top as tippy tops go. A moment ago, I said that I can do the same thing with my left hand, and you thought I was showing off where I was, but there was a scientific point to this. Now I'm going to spin it with my left hand, that is with exactly the same initial spin, but of the opposite sign. Instead of spinning like this, I'm going to spin the opposite sign, but that's the only difference. And when I do that, you see that axle tilts a little bit, so the top is trying to tip over. It's trying. You can wait, and wait, but you discover that it's not tipping over. You have in front of you what was the world's first, and for a long time, the only chiral tippy top, namely top which, when spun one way, tips over very effectively, but in the other way, it does not tip over. By now, we think we know how to produce this kind of phenomenon experimentally. I can design sort of hollow shells with wads of clay and so on. But there is no model, there is no theory. I think it's one of the nicest and probably the greatest open problems in classical mechanics. It's amazing that classical mechanics still has open problems that it has, and it's chiral dynamics. Now, in especially biochemical contexts, there has been an extensive study of chiral structures. You have heard of molecules which are mirror images of each other. One of them is okay, the other one is lethal, and so on. But chiral dynamics, with the exception of perhaps magnetic problems, which are kind of dictated by nature, there has been very little study of chiral dynamics. And this class gives you a taste of what it is like. So, as a little exercise, I'd like to share with you how to analyze the chiral, not chiral, but the tippy top. Here's my cartoon picture. You spin the tippy top, and this is what's happening halfway through. Theta is the angle of inclination between the vertical and axial of the top. And I'm going to assume, first approximation, that the angular momentum, the impulse with which I spun in the beginning, L, is more or less constant. Indeed, when you see the experiment, in the beginning it's spinning, and at the end it's still spinning quite well. So it's going to be taken to be constant. This is, in some sense, the zeroth order approximation that I'm sharing with you. Now, the point of this picture is the following. You see, divided by that blue line, blue arrow, angular momentum, left half of the picture in this convention is coming out at us, and right half is going into the plane of the picture. It's spinning and spinning. The point of contact is under the center of curvature rather than under the center of gravity. Center of gravity is the black dot, the center of curvature is the white dot. They are distinct. That's the characteristic of the tippy top. Because it's under the center of curvature, that's the part of the picture that's going into the plane of the screen. In other words, sliding is taking place into the plane of the screen. Friction, which opposes the sliding, is coming out at us from the plane of the screen. So friction is out of the page. But if you have a body of material like this and friction, you kick it with friction at the bottom, what's going to happen? Well, you're going to have introduced a tendency to spin it like this. That's called a torque. Torque, therefore, is horizontal and pointing leftward. when I say leftward, it's an approximation also. I'm assuming that the distance, separation between the center of curvature and center of gravity is not so large compared with the radius of the top, and that's another place where I use the zeroth order approximation. But modulo that, this is pretty much horizontal. Okay, so that's the torque. How does the torque affect this motion? Let's analyze how the component of the angular momentum along the axle changes in time. That's easy. You take ddt of L times cosine theta, and that's due to the torque. That change in time is due to the torque, so it's minus tau times sine theta. Why minus? Because the component is pointing in the other direction. Now, we have already introduced the approximation that L is pretty much constant. That's good news because we can take L out of the derivative and differentiate cosine theta. Wow, that's minus sine theta times theta dot, so we immediately get the theta dot to this approximation is tau over L. That's excellent news because it's positive. That means that the theta must increase, but vertical is fixed. How can theta increase? By making the axle tilt more and more. That's the mechanism. Torque from the friction, that's the mechanism for the tippy top. And if you plug in various numbers, you see tau comes from the friction, as we recall. So that's r, the radius times the friction, mu, constant coefficient of friction times mg, that's the weight, and L, the angular momentum, is equal to the moment of inertia, which has the dimension of mass times radius squared. So I'm going to write it as I hat, which is the dimensionless coefficient. For solid sphere, it's solid ball, excuse me, it's 2/3, and for hollow spherical shell, it's about it's 2 over 5. Not 2/3, 2 over 5, and for the shell, it's 2 over 3. But anyway, it's about 1/2 and times mr squared. And omega is the initial angular velocity with which I launched it, and that's positive. So let's estimate the tip over time in this zeroth order model. How does it tip over? Well, it tips over when theta changes by pi. That's when it goes up all the way. But you notice that there's something wrong in this analysis, namely that when you differentiate it in the first line, you divide it by sine theta. Well, what if sine theta is 0? Thou shalt not divide by 0. That's the 11th commandment. And theta is 0 or pi over 2 when sine theta is 0. So in the beginning and at the end of this motion, this analysis is not valid. This is an example of what people like Berlekamp call intermediate asymptotics. So only in the intermediate stage is this valid, but we hope that this is going to capture the essential science of the toy. So in order for this tip over to happen, you have to change theta by pi and at the rate theta dot. So I'm going to divide pi by theta dot. Let's do some orders of magnitude estimate. What is theta dot? I've already put that down, and there's a cancellation. You know, one factor of r cancels and m cancels. So what we have to estimate is pi times I hat times r omega over mu g. What are those things? I hat, we remember from school, is about 1/2. Okay, 2/3, 1/2, whatever it is. What is r? R is the radius of this object, and I think that's going to be about 2 centimeters. I went home and measured it, and it's about 2 centimeters. By the way, do people speak metric in this? Yeah, do. Okay. Now, omega is quite difficult, so I'm going to come back to that. Mu is the coefficient of friction between, say, glass and wood. And there's a good way to measure what it is. You just start tilting the support until the thing starts slipping. That critical tangent turns out to be mu. Okay, that's the static friction rather than dynamic friction. But the difference between them is not all that great, so I'm going to adopt the static friction. That's 1/3, because the tangent is about 1/3, and we know G is 980/1000. Oh, why is that? Because we're working in centimeters rather than meters per second. What about omega? Omega is the angular velocity. That is how many times it spins per second times 2 pi. So I'd like to have a sort of vote. How many times do you think, sorry, not that one, coming, is that the stage video? No, camera, I'm confused, so I think this one. How many times per second does it spin? That's very difficult to estimate. It's pretty fast, you know. Oops, excuse me, 1 second is a long time. 1, 1, 1, 1, 1, 1, 1. How many times? Well, I think it's clear to all of us. Yes, there's some vote? 20? Okay, so I completely agree that it should be somewhere between 10 and 100. I mean, 100 is way too large and 10 is way too small. So we are going to take the geometric mean between the two of them. Why geometric mean? Because we are multiplying those numbers. So in a multiplicative problem, average should be the geometric mean, not the arithmetic mean. So we're going to say 20, 30. Well, we might be off by a factor of 2, all right, times 2 pi. So pi times time is, of course, about 10, and so on. When you do all the cancellations, it comes out to be about 2 seconds. Let's see what the experiment shows us. 1, oops, what's this? 1, 1, 1, 1, 1, 1, 1, so 1, 1, 1, 1, just under 2 seconds, I would say. Pretty good for something like this, huh? Okay.
You can also see that it's pretty linear, right? I mean, you can see it moving, and it's moving in a more or less constant.
That's right. And then something happens in the beginning. That's right. So it's intermediate asymptotics is in fact successful. And you can do a much sort of finer theory, and you can justify all those approximations that I swept under the rug, it turns out. But that's for another. Okay. Now, those were individual objects. Now I'd like to show you a collection of objects. We are somehow going gradually towards statistical considerations. Here is a ball that I borrowed from Cambridge, England, Cambridge University cafeteria. And you see a box marked Chai Gruzinski Extra, which I bought from a Berlekamp in Bordeaux. And it's an extra Georgian tea box. And when you open it, maybe you cannot read this, but there's a very detailed scientific instruction, how to brew the best quality of tea, and so on. And use. But that has nothing to do with my experiments. I carry around cedar balls inside. And one thing that you can say about this experiment is that it smells nice. I mean, how can you say that about many other experiments? So if I put a few cedar balls and I swirl this, you see that the cedar balls circulate in the same direction that I'm swirling. By swirling, I mean doing this. I don't mean this. I'm not rotating anything. I'm in the translation subgroup, if you like, of the Euclidean group, but that happens to be periodic. I'm doing this. Okay. So they circulate in the same direction. Now, let's increase the crowdedness or the density of the cedar balls. And when I swirl, you see that cedar balls circulate in the opposite direction. Do you see that? So there was a transition. It's a bit like a phase transition. With 1 ball, 2 balls, 3, we have seen circulation is in normal direction. But with 4 balls, there's a little bit of hesitation, but still normal. But at 5, there's a lot of hesitation, 6. And from 7, it's pretty clear that the circulation has reversed, 8. And it turns out that this is a bit like a transition from gas to liquid. Indeed, when there are few of those, you see what's driving this motion is that the wall keeps bumping into those cedar balls, and cedar balls are effectively independent particles because there are few of them. And so they are driven in the same correct direction. But when the crowdedness increases, all those contacts start mattering. And what happens is that the wall rubs against the cedar balls. And each cedar ball rotates, and because they're in contact with the neighbors, they start rotating the neighbors and so on. So from the linear momentum-dominated world to, if you like, angular momentum-dominated regime. And it's a bit like the transition, as I say, from gas to liquid. Liquids can sort of move against each other, but still they are very tightly packed together, whereas gas, of course, moving around. And to show you that it is really like that, if you keep increasing the density, then it freezes solid. Okay, that's what it is. This was discovered by Rayberg and analyzed by Palfi-Moret several years ago. Now, that was the transition, kind of phase transition that you can see. But now I'd like to produce transition of a much harder kind. Those two heptagonal wheels were produced and given to me as presents by Andy Ruina of Cornell University. And many years ago, I used to go around saying that this kind of phenomenon should exist, but I couldn't believe it when I received those. So those heptagonal wheels, I can guarantee, are made of the same material, same alloy, treated the same way on the surfaces. They have the same mass. Also, I'm going to say something tricky. The mass distribution within each is uniform. In other words, the density function is constant. In other words, I'm not hiding anything. You see there are spokes and so on. I'm not hiding some hollow inside. It's not true that there's more mass near the rim and so forth. There's none of that. What you're seeing in volume is exactly how the mass is distributed. All right? However, when I try to roll one of them, it rolls very, very smoothly, very nicely. But the other one refuses to roll. They look the same. But there's a dramatic difference, qualitative difference, in the way they move. How can that be? Same mass, distribution is uniform, and same surface. Any ideas?
So is the shape in which the inner holes are cut exactly the same?
Well, I don't know. Do you think they are? I'm going to show you on the stage video. That's two of them, They look exactly the same to me. But the gentleman said shape. Indeed, that's one thing that I didn't say was the same. It turns out that these are not heptagons, or one of them isn't. The one that rolls is a heptagon that has been bulged out ever so slightly on each edge. And the one that does not roll is a heptagon. Why does that make the difference? Here's why. And what happened to the... Here, okay. And each time. You see, this is the one which has been bulged out a little bit. When it has been bulged out, imagine that this wants to roll from one vertex to the next vertex. And as it does so, there is a continuous transition of the point of contact between the two. So it can go from one vertex to the next vertex as the thing rolls without any loss of energy. You can continuously transit. However, suppose, and that's true, however small the bulging is, let's call the bulge epsilon, and for every positive epsilon, however small, this continuous transition is allowed. However, consider a case when epsilon is strictly 0, that is, when you have a straight regular heptagon. Then, while you are trying to roll from one vertex to the next, there is no point of contact in between. That is, you're pivoting around the previous vertex, and the entire edge in the meantime is in levitation. It's in the air and going down until, bang, it comes in perpendicular shock to the surface, and there dissipates the entire energy and kills the motion. So that's a discontinuous passage which dissipates everything. And what is amazing is that this is true when epsilon is 0, but for every epsilon positive, it's not true. So here we have an example of one of the main difficulties of applied mathematics and, in fact, challenge of mathematical sciences, singular perturbation. In other words, you have a family of models depending on epsilon, say, parameter. For every epsilon, not 0, you have some qualitatively reasonable prediction, but at 0, you break. And of course, you all are aware that the most famous example is Navier-Stokes. And when the viscosity goes down to 0, or a bit more precisely, when the Reynolds number goes down to infinity, the implicit limit that you see when Reynolds number is infinity or viscosity is 0 has no relation, for example, potential flow, to the limit as the viscosity becomes smaller, but not 0. You get huge turbulence. But this is probably the world's smallest number of degrees of freedom example of singular limit, and you can see it in front of us. It's a wonderful thing. I can tell you later on why we have a heptagon rather than something else, but let us get the move. Okay. Next, that was the singular limit. Oh, by the way, before we go on, I'm going to have a little comical interlude. Speaking of reversing the direction and so forth, here is a nut and bolt, very loose, and this is an electric toothbrush, the cheapest I could find in Princeton. And when they get going, it vibrates. Now, unfortunately, this end goes back and forth, but that has nothing to do with the physics I'm going to show. If you have a purely vibrating electric toothbrush, it works too. But anyway, if I put this vibration against the bolt, I mean, it's going to make the whole thing vibrate, but there's no reason why you would break the chiral, you would break the rotational symmetry. However, if I channel my oriental energy into this, I can make it go one way. Notice that it's going against the gravity, or I can make it come back this way. Huh? This way, or this way. And in fact, I can keep going against gravity so much that I can undo. You can do it, you can do it. It's really resisting. Okay, come on, okay. Thank you very much. I mean, okay. 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 Let's move on to the next thing. Good. The mirror. Does anybody have a coin, please? Thank you. Any coin will do. Thank you, David. Thank you very much. So, when you drop a coin, can you hear in the back? Can you hear? You hear this characteristic shuddering noise. So characteristic that if you hear this in a cafe or bar or restaurant, you know that somebody has dropped the coin. Okay, I'm going to seriously return it to Monsieur le Directeur. Okay. Now, here is an exaggerated coin. It's huge and it's very heavy. And I'm going to let Elwyn wait. It is heavy. Yes?
What am I doing?
You're just going to confirm that it's heavy.
Oh, yeah.
Yeah, it's very heavy. Thank you very much. It's very heavy. Okay. Because it's heavy, when I launch it, you can see lots of details of this motion that escape our attention. And it will keep going for a long time. It's doing this motion purely by inertia. I'm not driving it underneath, or there's no magnet or anything. There's no engine. It's going and going. And while it goes, you see that something is accelerating. Going faster and faster. But note that the picture on top shows that the rotation is not accelerating. Something else is accelerating. Faster and faster. It's, so to speak, the flapping motion, which is superposed on the rotation that's accelerating. Faster and faster, it's actually lasting longer than I thought, but it goes on and on, it goes on. Do I have enough time during the lecture? Goes on and on. But it will soon come to a halt, and when it does, I invite you to watch, but also to listen to the pitch that the disc gasps at the end. Amazing, no? Something has diverged. I mean, zzz. You can do the same thing on the table. Maybe it's less impressive. More than 10 years ago, this has attracted a lot of attention, and I was a postdoc in Montreal, not unfortunately postdoc at MSRI, which I would have loved to. I think you would have done a good deal of good for me. But I had already worked out a simple model of this, but there were lots of papers around, and one of them appeared in Nature claiming that this motion has to do with the friction of the air trapped underneath the disk. Now, people didn't like this, so there was a team, I think writing from Berkeley, of all places, saying that they did the same experiment in a vacuum chamber, but saw essentially the same kind of motion. Of course, not the sound, it's because it's vacuum, but essentially the same kind of motion. Anyway, for a number of reasons, this is a tricky problem. In Montreal, I wanted to sort of verify my model and also do an experiment, but you know, vacuum chamber is very expensive for a postdoc. So I went to a ladies' accessory shop and bought this. Can you focus, please? Yeah, thank you very much. Ladies' accessory shop and bought this. A ring. You see, there's no question of air trapped underneath the disk because there is no disk. And I'm going to launch it in a very nice way. I spun it in a vertical position. It's like a ballerina who's standing up and is spinning and spinning. And this is, you might say, the first phase of the motion. But soon there will be a transition. It's almost a very sudden transition to the second phase. It's still, because ballerina will become tired. Okay? It's still standing up. Standing up, that's still the first phase. But when the ballerina becomes tired, she decides to transit to another motion. There. And that was sudden. And that's the second phase. And the second phase is entirely analogous to what the disk is doing. It's not going to go on for a long time because it's much lighter. Inertia is important. But it's exactly the same motion. Okay, so the air has nothing to do with this. I'd like to then show you what it has to do. And we shall model this by thinking of the motion as a superposition, as I mentioned, between a spin and this flapping motion. Now, here is the picture. The picture is that when you drop a ball, it goes bong, 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 bong. It bounces many times, and in an ideal scenario, you know it's a calculus problem. It bounces infinitely many times, but comes to a stop in finite time. So the frequency of the bounce is diverging. How does the frequency of this bounce, boom, 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 diverge? You can understand it in the following fashion. The energy per each bounce has to do with the height to which the bounce rises. Of course, that's the potential energy, if you like. But the height is proportional to the time that it falls raised to the square, because it's in a uniform gravitational field. T squared is proportional to the height. But time is 1 over frequency, so the energy of each bounce, nth bounce, increases like the bounce frequency to the negative second power. That's the picture that we should bear in mind. At the same time, what is causing dissipation or the energy lost in this case, the regular and this disk case? Well, there have been many theories, but the friction of the air underneath the disk, lubrication, has nothing to do, as we verified. There are many other possibilities, and I'd like to show you one of them. One of them is the point that as this point of contact goes around and around, that's also the point of pressure that's going around and around. And as a result, the whole support is made to vibrate. That vibrational energy, or if you like, the wave of vibration, goes off, phonons go off, carrying off energy which is lost to the system. In order to convince ourselves that it is important, let's do the experiment on a good absorber of vibration energy, such as my hand. Human bodies, especially mine, have been designed to withstand lots of shocks. So please pay attention to how long the experiment lasts when I do the experiment on my hand. That's it. The entire energy escaped through my body to the ground. Effectively, we have earth to this system. So that kind of dissipation is at work, and it's quite reasonable to believe that if you take the time to the singularity, I call it T sing because it sings, you see, T singularity sings. That's minus time derivative of E, but that dissipation rate of the energy is proportional, varies like the flapping frequency. Now, if you identify the flapping frequency with the bounce frequency, that's the picture, then you see that frequency is minus half power of E, so you have a differential equation there. And solving that differential equation, very easy stuff, you get that the energy to the 3 over half power is proportional to the time to singularity, but we know what the energy was in terms of frequency, so you get to the conclusion that frequency should diverge as you come closer and closer to the steady singularity to the power minus 1/3. Well, Ariel Amir of Harvard University, he's a junior fellow at Harvard, recorded the system, and this is the graph. For some reason, the time is plotted from right to left, because I think in Israel you write from right to left, right? But anyway, so that's how the time goes. But the slope that you see in the red is minus 1/3 slope. It's a log-log plot. And look how beautiful it is. I mean, you can't really get this kind of beauty in experimental data nowadays. But it is exactly minus 1/3, and that's how the system diverges. This kind of negative 1/3 divergence is, in fact, quite universal. Whenever you have sort of multiple bouncing system, bam, 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 and then you get the divergence, or anything that's similar, you get negative 1/3. Here's an example. You can see, I think maybe I should do it here. Those are two very strong magnets made of neodymium, and when I release, they do that. I can toss them in the air also. Yeah, can you see? You can hear the divergence, and that is negative 1/3 as well. So scaling law pops out from this really simple analysis and a very universal behavior of all kinds of divergence. Okay, it is time to conclude this show. So I'm going to give you one last toy. Here is the toy. It's a wrinkled ball from Japan. It's a traditional Japanese toy. Maybe other cultures have also this kind of thing. There's a hole there. And the way you're supposed to play with it is to blow air into the hole and inflate the ball, and then play with it. Note that once the ball has been inflated, it has an effective elasticity. You know, it's quite bouncy. Although paper is made of very wrinkly paper with no elasticity, but it bounces. But there is another really interesting way to inflate this. I'm going to wrinkle it, and please allow me a minute or so. I'm going to keep hitting it. Now, when you hit something, don't you have the impression that you should be making that something smaller and smaller because you're denting it? Huh? When you hit something, surely you make it smaller. But as I hit, look what's happening. It's become completely round. This is a way of making something larger by hitting on it. How does that work? My first idea was the aspect ratio argument. You see, if you have something that's really flat and really sort of skewed, if you hit it in already the flat direction, it doesn't change its shape. But if you hit it in the perpendicular direction, it's going to make it a little rounder. Okay, so on average, 1 out of 2 times, you're making it rounder and rounder. But this argument has lots of faults and defects. For example, how do you explain that once round, it's stably round? It's a stable equilibrium, stable attractor, universal attractor, and it keeps round. Aspect ratio argument would predict that it becomes less round, 1 out of 2 times. And also, you see, this air has to go in and out. And you cannot get the air in and out very, very quickly. Besides, that's presumably why you get this bounciness when you do this. So that's not really the issue. I think what's happening is the following. The key is what you're going to see. When I wrinkle it and release it, watch what happens. Sorry. You see, this starts fighting back. Not all the way back. It doesn't have perfect memory, but it becomes a little rounder. This is what is called viscoelastic behavior with a little memory, but not quite. And I'm going to show the analysis. The idea is that, you see, imagine that you have this wrinkled thing, wrinkled on both sides, and you hit one side. When you hit on one side, that side that you hit gets wrinklier because you sort of destroyed some patterns. But the other side, because the air that propagates and poof, gives it a kick or a push, a shock on the other side becomes smoother, rounder. But you see, so on the left-hand side, it got wrinklier. On the right-hand side, it got smoother. But then the viscoelasticity kicks in until it's the next time, the wrinklier side starts fighting back. So per this cycle, you have increased effectively the smoothness on the right, but you didn't lose. It's the same wrinkliness on the left. So per cycle, you have made the whole thing smoother, and you keep going. As a result, when you plot the volume as a function of time, I'm pretty sure this is what's going to happen. You get this zigzag pattern. Each time you hit, you are instantaneously decreasing the volume, but then it recovers a little bit because of this viscoelasticity. Hit, recover, and you asymptote this perfect spherical shape. What is quite remarkable about this is the following. You see, when you have many, many different scales cohabiting the same phenomenon. That happens all the time in physical sciences and mathematics. You have often large scales, middle scales, smaller scales, and so on. And in typical examples, in fact, almost all natural examples, there's an energy flow or information from the large scale to the smaller scales. The most famous example is called Mogorov's scaling law in turbulence. From large vortices to middle vortices, small vortices, even smaller vortices, smaller and smaller scales are getting the sort of manna from heaven, from up to down, and that's what's feeding the small vortices and keeping the turbulence going. But in this case, you see, in the beginning, there are lots and lots of small wrinkles, and at the end, there are very few large wrinkles. So you have the inverse cascade from small-scale wrinkles to large-scale wrinkle. And there are very few examples in naturally physical phenomena of inverse cascading, and that's very interesting to see. Let me conclude the whole thing by saying that we have covered lots and lots of ground, amazing expanse of grounds with those simple toys, chiral dynamics, friction as a creative agent, and phase transition of some kind, singular perturbation, finite time singularity, viscoelasticity, and inverse cascade, and all that. So all these wonderful variety of mathematical sciences bring us to the essential question. Why are we playing with toys? In manner of answer, I'd like to tell you a story quote a story from a relatively unknown book of Aristotle called De Partibus Animalium. It tells of famous philosopher, natural philosopher, Heraclitus. He was the leading thinker of the time, very famous, a bit like Elwyn Berlekamp of 600 BC. And two young visitors come to see him. Aristotle says in this passage, in all natural phenomena, there is something of the marvelous. There is a story that some visitors once wished to meet Heraclitus, and when they entered and saw him in the kitchen, warming himself at the stove, very homely ambiance, whereas they were expecting him, in a big lecture theater or dignified robe and so on, they hesitated. But Heraclitus said, "Come in, don't be afraid. There are gods even here. Enagar kai entausa theus." To all of you gathered today, and especially to David Eisenberg, and above all to Elwyn Berlekamp, I wish you the great future of MSRI, and thank you very much.